Hello, everyone. This video is about symmetric matrices, and in particular, we'll talk about the properties of their diagonalization. So symmetric matrices are tightly related to orthogonal matrices, and here's the reason why. We've been thinking about orthogonal matrices recently, but let's see what happens when we have a diagonalizable matrix with a matrix P that is orthogonal. So I remind you that diagonalizing a matrix, well, a matrix being diagonalizable it means that the matrix is similar to a diagonal matrix. So this D is diagonal and this P is an invertible matrix. Similarity just means that A can be written as PDP inverse. We can say a little bit more when the corresponding matrix P is orthogonal. So remember from the discussion we had last time that orthogonal matrices are matrices for which the transpose and the inverse coincide. So if A is diagonalizable with orthogonal matrices, so when P is orthogonal, we can write the following. Well, we can look at the transpose of A, which is the transpose of P, D, PT, because A is PDPT, because PT is P inverse. When I transpose this, I have to transpose everything and switch the orders. So I get PT transpose, D transpose, P transpose. But now transposing a matrix twice is the same as not doing anything. And D transpose, it's a diagonal matrix. When you transpose it, you get back itself. So D transpose is D. In other words, you see that A transpose is at the end of these inequalities exactly equal to A. What we proved is that A and A transpose are the same, so our matrix A is diagonalizable. This is the upshot. Oops. If a certain matrix A is diagonalizable using orthogonal matrices, then A must be symmetric. The only possible matrices that are diagonalizable with orthogonal matrices are symmetric. And the most astonishing thing that happens is that the converse is also true. And the converse goes under the name of the spectral theorem. I'll comment on the name in a second. But this theorem, it's also called the theorem on diagonalization of symmetric matrices. Every symmetric matrix is diagonalizable, and it is diagonalizable with an orthogonal matrix, which is the converse of what we showed above. We just proved that matrices that are orthogonally diagonalizable are symmetric. This theorem tells us that all symmetric matrices are orthogonally diagonalizable. And it's amazing if you think about the fact that it's really hard to diagonalize a matrix. If you think back about when we had to diagonalize matrices, that took work. You have to look at eigenvalues and count their multiplicities and look at the dimensions of the eigenspaces to know if you could diagonalize it. This theorem gives you an incredible shortcut, which is if your matrix is symmetric, then it is diagonalizable. Of course, there's non-symmetric matrices that could be diagonalizable themselves, but that's outside the scope of this theorem. It's an incredible shortcut in the case that your matrix is symmetric. If it is symmetric, you know already it's diagonalizable, and moreover, you know that you can diagonalize it with an orthogonal matrix. I'll just comment very briefly on the name spectral theorem. The terminology of a spectrum is, well, the spectrum in linear algebra means the set of all the eigenvectors, of all the eigenvalues of a matrix. And this terminology comes from physics, actually, because some of the early quantum mechanicists realized that they could express the spectrum of frequencies that was projected out across an atom of hydrogen as a set of eigenvalues of a certain operator. So they started calling spectra this set of eigenvalues. It's not important, but I always thought it's a funny name, so I figure I'll tell you where it comes from. Okay, yeah. that's it for the theorem. We'll see an example, but before doing that, let me just comment on the following remark, which is something that is sort of implied by the theorem, and we can actually have an idea of why this is true. The eigenspaces of an orthogonal of a symmetric matrix are orthogonal between one another. I mean, it's implied in the theorem because the theorem tells you that the matrix P is orthogonal, but P is the matrix whose columns are eigenvectors of A. So in other words, what the theorem is saying here is that there is a basis, there is an orthonormal basis of eigenvectors of a symmetric matrix A. That's what it means to be diagonalizable with orthogonal matrices. And okay, let's have a look at this fact. If a matrix is symmetric, then its eigenspaces must be orthogonal with one another. Let's see why that's true. Suppose I take two different eigenvalues. So I take two distinct eigenspaces, and I take distinct eigenvectors. So maybe I'll do U and V such that U is a lambda1 eigenvector and V is a lambda2 eigenvector. So they live in different eigenspaces. Okay, so then when I compute this quantity here, AU.V, I can go down two different ways of computing it. Once I could just take A times U and use the fact that U is an eigenvector. So I get lambda1 times U.V. Or on the other end, I can move the matrix across the dot product. When I move it across, I have to transpose it, but we're assuming that the matrix is symmetric. So when I get to this side, I can use the fact that V is an eigenvector and factor out a lambda2 U.V. Okay, so how can this happen? What we proved here was that lambda1 U.V is equal to lambda2 U.V. However, lambda1 is different from lambda2 from the assumption we're working with different eigenspaces. So the only way that this can happen is that U.V is equal to 0. And so the eigenspaces are orthogonal. As I said, this is consistent with the theorem because the theorem tells us that there's an orthonormal basis of eigenvectors, so the eigenspaces better be orthogonal with one another. Let's have a look at one example. There's this matrix A. You can see it's symmetric. And I did some computations before. So the goal of this example is to find the matrix P and the matrix D so that A is diagonalized with an orthogonal matrix. It takes a little bit of work. So to get there, we can compute the eigenvalues, and you see that the eigenvalues are 0 and 18. 18 has multiplicity 2 from the characteristic polynomial. Knowing the eigenvalues already tells us that the diagonal matrix that A will be similar to is a matrix that has exactly the eigenvalues repeated with multiplicities on the main diagonal. What's left to determine is the matrix P. We want for P 3 linearly independent eigenvectors that are orthonormal to one another. So we want them to be orthogonal and we want them to be a unit vector. Okay. It's not too hard to see that, well, you can find an eigenvector for the lambda 0 eigenvalue. To find this W1, all I did was to solve A minus 0, the identity. times x equals 0. So in other words, W1 belongs to the null space of A, because A minus 0, the identity is A. So you find that this is not going to work for your orthonormal basis of eigenvectors because its norm is bigger than 1. So what we want to do is to normalize it, and we'll divide by the norm. The norm of this guy is the sum of its entries squared. So we get 16 plus 1 plus 1, that's 18. One over root 18, negative 4, 1, 1. Okay, so that's a unit eigenvector, RV1. Let's work with the other eigenvalue, lambda equals 18. This is multiplicity 2. So, well, yeah, we'll have to work a little bit more. At a minimum, we know that we need to find 2 eigenvectors. Let's see, let's get on with that. To find eigenvectors, again, we want to look at the null space of A minus 18, the identity, which I'll write here. So it's negative 16, 4, 4, 4, minus 1, minus 1, 4, minus 1, minus 1. Okay. Now we want to find vectors in the null space of this matrix. And you can solve the linear system and reduce it to row echelon form, but you can also stare at it and notice that maybe the first column and the first column is equal to minus 4 times the second column. In other words, if I add the first column and 4 times the second, I get 0. So this vector u2 that I wrote here, 1, 4, 0, is in the null space here. In other words, it's an eigenvector of the eigenvalue 18. Another possible eigenvector that I can see from here is that the second and third column are the same. So if I take 0, 1, minus 1, well, that'll give me 0. So it's an eigenvector of this matrix. There's no reason why these 2 eigenvectors that I just got by staring at the matrix are orthonormal to one another. In fact, they're not. If you dot them together, you get 4. Which is not 0. So they're not orthogonal to one another, which means that we have to use a Gram-Schmidt orthogonalization process. Let's do it. Well, the Gram-Schmidt takes in as an input a basis of the null space of A minus 18i and spits out an orthogonal basis. So the first vector of the output, I'll call it W2, will be just the starting vector u2. And then W3 can be computed as follows. The recipe is this. I take u3 and then I project u3 down along W2, the previous one, and I subtract that projection. So let's do that. Here we get 0, 1, minus 1, minus, now we have to do some dot products. u3 dot W2 is 1 times 0 times 4 times 1 plus 0 minus 1. So that's a 4 here. And the norm square of W2 is 18. We computed the norm of whoops. No, we didn't do that. The norm square of W2 is the sum of the squares of the entries, which is 1 plus 16. So this is 17. And then I will have to subtract W2, which is U2, 1, 4, 0. So when I compute that, I get, let's see what's up here. That's a minus 4 over 17. Then I have 1 minus 16 over 17 and negative 1 over here. Okay, if I clean this, I get minus 4 over 17, sorry. 1 over 17 and minus 1. Okay. Let me pause for a second and I'll double check if these computations are correct. Okay, the computations are correct. You can do a quick check that the vector W2 and the vector W3 defined like this give you indeed 0 when you dot them together. Okay, so now we found two eigenvectors that are orthogonal to one another. The next thing we need to do is to normalize them. And maybe, yeah, we'll do it in a second. Let's see. So V2 will be my W2 normalized. We computed the length of W2 here. So this would be 1 over square root of 17 times W2, which is 1, 4, and 0. And V3 will be whatever the normalization of this is, which, well, I want to do it, but just for my comfort, I'll write this leaving the 1/17th out. So when I write that, I get -4, 1, -1. So the length of V3 will be, so here I'll have to do W3 divided by the length of W3, which will be, let's see, I'll have the vector 4, 1, -1, and then I'll have 1 over 17 coming from the W3 up here. And then I'll have to divide by the length of W3, which will be the length of this vector -4, 1, -1, which is, let's see, the sum of its squares, which is square root of 18, divided by 17. So these will cancel each other out, and I get that unit vector. Maybe that was more complicated than necessary, but there it is. Okay, so we're finally ready. So after normalizing, we have an orthonormal basis. Maybe I'll write it here. V2 and V3 are an orthonormal basis of the 18 eigenspace. And V1 is an orthonormal basis for the 0 eigenspace. When I put them together in this matrix, let me go back and check what they are. 1 over root of 18 -4, 1, 1. So I get -4 root of 18, 1 over root of 18, 1 over root of 18. That's my V1. Then I'll have V2, which I've written here. It's 1 over root of 17, 4 over root of 17, 0. And then I have V3, which is -4 over root of 18, 1 over root of 18, -1 over root of 18. I encourage you to check that this matrix is in fact orthogonal. But it should be right. I mean, it will come out of the computations that we did in this example up here. So that's the conclusion of the example. In this example, we picked a symmetric matrix and we diagonalized it using not only an invertible matrix, but an orthogonal one. We found an orthonormal basis of the eigenvector. And that's something that you cannot do unless your matrix to start with is a symmetric matrix. In the next video, we'll see some applications of this orthogonal diagonalization of symmetric matrices.